Hello and welcome to this short presentation in which I'm going to talk about the central limits for generalized descents and inversions in permutations and finite Weyl group elements. Let's start by giving some basic definitions along with a simple example. By sum n we mean the symmetric group containing all bijective functions from the set of natural numbers between 1 and n into itself. And to give an example of a permutation written in one-line notation, we chose pi to be equal to 253146. And note for the following definitions that we take pi of I to be the notation for the ith entry of a permutation. In this case, for example, it's pi of 1 equals to 2, pi of 2 equals to 5, and so on. For the elements of the symmetric groups, two very well-known statistics are called inversions and descents. And taking a permutation pi of length n, a pair I, j with I and j between 1 and n, and j being greater than I, is called an inversion of pi if and only if pi of I is greater than pi of j. And taking a look back at the example once again, one notices that, for instance, the pair 2, 4 is an inversion because pi of 2 equals 5, and that's obviously greater than pi of 4, which is equal to 1. And similarly, a permutation has a descent at position I if and only if pi of I is greater than its right neighbor, pi of I plus 1. So for the descents, we just compare an entry with its directly right neighbor. And for the example, one notices, for example, a descent at position 2 because pi of 2 is obviously greater than pi of 3. Another way representing the symmetric group is using the concept of Weyl groups of type an-1. Such Weyl groups come with a root poset from which we chose the positive roots to be the set phi plus containing elements of the form ei minus ej, where ei is the ith standard vector in R to the n. An easy representation along with a natural order on these elements is seen on the left-hand side as a root poset of type A5. Transferring permutations into this context, one notices that a permutation pi acts on an element of phi plus by permuting the entries of the vectors. That means pi of the element ei minus ej is equal to e pi of I minus e pi of j. And again, linking this with the definition of inversions already seen before, it follows that an inversion I, j of pi is equivalent with e pi of I minus e pi of j not being an element of phi plus anymore, because it does not fulfill the defining property for being an element of phi plus anymore. Same arguments can be used to transfer the definition for I being a descent of pi to the fact that pi of ei minus ei plus 1 not being an element in phi plus. To make it even more vivid, let's look again at the root poset on the left, because if considering the statistic of inversions, one needs to involve all roots of the root poset, because every entry of a permutation is compared to all entries of its right side. And in the other case, being interested in descents, one only considers the first row of elements within this root poset, which are called simple roots. These two permutation statistics are very well known to fulfill the central limit theorem, so let's make it more formal by defining the corresponding random variable x sub beta of a permutation pi to be the indicator variable for the property of pi of beta not being an element of phi plus, which of course is the same as asking whether pi got an inversion at I, j. And a summation over a given set A of positive roots gives us the random variable x sub A of pi, which counts the total number of inversions for a given permutation due consideration of the chosen subset A of phi plus. The question one might ask now is for which subsets A of phi plus this random variable fulfills a central limit theorem. We've seen that in case of capital A containing all roots, the statistic of inversions is represented, and the CLT was proven by Bender in 1973 already. For capital A containing all roots within the first row of a root poset, the statistic of descents is represented, and the CLT was proven by David and Barton in 1962. It's very important to mention that not every general subset fulfills a CLT. For example, if you take the very left diagonal of a root poset, it's easy to check that the corresponding random variable is uniformly distributed. So, first step we took for generalization is taking all roots up to a given height, or taking just one complete row of roots at a given height. For the first case, we call it the generalized inversions. A CLT was proven by Bohner, for example. And the second case we call generalized descents is currently joint work with Christian Stumm. Moving one step further and finally reaching the second part mentioned in the title of this presentation, these statistics can be adapted to general finite type Weyl groups. Besides permutations, there are signed or even signed permutations you can think of as other examples. The statistic of inversions and descents were already investigated in this more general setting by Kahle and Stumm, but the generalizations of these are again still work in progress together with Christian Stumm. And finally, I want to talk about the sketch of the proof for the simpler case of considering permutations again. As we are interested in the variance and as we are considering a sum of random variables, we started analyzing the dependency between these variables x sub beta of pi. It turned out that in case the indices of two given roots, for example ei minus ej and ek minus el, if those indices intersect, the corresponding variables are dependent. The concrete value of the covariances, especially its sign, is still dependent on other criteria of the chosen roots. The then following calculation of the variance is based on counting the number of dependencies for each element within the chosen subset A, and analyzing whether they add a positive or negative covariance. So the results for the variance of generalized inversions and generalized descents are written down here, and they were used along with a theorem by Bohner, which is based on building a dependency graph to prove the existence of the central limit. And for the very last, I will give some short comments about the situation in general finite type Weyl groups. In these situations, the analysis of the covariance requires more general Coxeter theoretic arguments, and it leads to even more case differentiations. The same holds for the calculation of the variance, for which a great number of case analysis is needed, although the main procedure remains similar to the one explained before. And this finished my short presentation about the central limits for generalized descents and inversions in permutation and finite right group elements. And I thank you very much for your attention.